In the last several chapters, we've learned a number of different shortcuts for taking derivatives quickly. We've learned formulas for power functions, exponential functions, trig functions, and log functions. And then we've also learned the chain rule and the product rule, how to take derivatives of certain types of combinations of those more basic functions. In this video, I'll do a few examples showing how these rules can be combined. So let's start with, let's say, the function x squared sine x cubed. So suppose we want to take the derivative of this. So there are two things going on here. There are two functions multiplied together, x squared and sine x cubed. Right, so it's just this function times that other function. So we'll need to use the product rule. But then this function here, sine x cubed, that's a chain function, a function of a function. You do x, you cube it, and then you sine that. So we'll need to use both the product rule and the chain rule in this case. So let's see how that goes. So f prime of x. So we start with the product rule, and you take the derivative of this one and leave that one alone. The derivative of x squared is 2x, and I leave this one alone. Sine x cubed stays sine x cubed. Then I need to leave the first one alone and take the derivative of the second one. So leaving the first one alone, x squared just stays x squared. And then I have to take the derivative of sine x cubed. So x cubed is the inner function, which we often call blah. So the question first is, what's the derivative of sine of blah? And the answer to that is cosine of blah. So we just leave blah as blah. But I'm not done. I then need to take the derivative of the inner function. The derivative of x cubed is 3x squared. So this simplifies a little. I could turn x squared into x to the fourth. But there's not much simplification that can be done. So typically, when one takes a derivative, the answer is larger than the function, larger than the function you started off with, larger in that it takes more ink to write. And there's not always a lot of simplification that can be done. So this example showed a product with two functions where one of those functions involved the chain rule. Let's do another example. This time the function is cosine x over 1 plus 2x. So this situation is not a product, but a quotient, but we can turn it into a product by rewriting this as follows. This is cosine x times 1 plus 2x to the minus 1. So I'm just using the exponent rule, 1 over, let's write it out just as a reminder, 1 over y to the a is the same thing as y to the minus a. So that's just a general property of exponents. So I rewrite it this way, and then I have a function times another function, and I can use the product rule. There is a quotient rule. I think it's a pain to remember, and it's not particularly simple, so I just like writing it this way. You'll get the same answer either way. So now let's take the derivative, and we're again going to have to use the product rule and the chain rule, because this function is a chain function. I take x, double it and add 1, and then I raise it to the minus 1. Okay, so let's do the product rule. Take the derivative of the first one, leave the second one alone. Derivative of cosine is minus sine x. Leave the second one alone. So we're halfway done. We've done the first half of the product rule. Now I need to take the derivative of the second one, leaving the first one alone. So leaving the first one alone, cosine x stays cosine x. And then I need to take the derivative of this. So there's an inner function, 1 plus 2x, and an outer function, something to the minus 1. So the inner function we call blah. So the derivative of blah to the minus 1, well, that's a power function. And the derivative of that, I bring down the minus 1, blah stays blah, and upstairs is minus 1, which is minus 2. But we're not done. We need to take the derivative of the inner function too. The inner function that is 1 plus 2x, that's what we were formerly calling blah, and the derivative of 1 plus 2x is just 2. So this whole thing becomes minus sine x, 1 plus 2x to the minus 1. I can bring this minus 2 out front. Minus 2 cosine x, 1 plus 2x to the minus 2. Now you can simplify this further if you want. There's no need to do that. So for the homework, you can get here, or really even here, and you're done. You've found the derivative. But let me just do one more step. I can take these negative exponents and put them back downstairs. Minus sine x, 1 plus 2x, minus 2 cosine x, 1 plus 2x squared. And if you're feeling really ambitious, or you just have some spare time on your hands, you could put these over a common denominator and simplify further. So, and often that's how the book is going to express their solution. Again, there's no need for you to do it, but if you wanted to, you could. It's just a chance to practice some algebra. And so to put things over a common denominator, I'll do this just for the sake of being complete. I'm going to multiply this term by 1 plus 2x over 1 plus 2x. 1 plus 2x over 1 plus 2x. So that's a valid move. This term in blue or turquoise, whatever this is 1 in disguise. I can always take a fraction and multiply it by 1. Doesn't change it. So then if I carry out this multiplication, I'm going to have, let's see, I need to distribute the minus sign. Minus sine x minus 2x sine x, 1 plus 2x squared minus 2 cosine x, 1 plus 2x squared. So now I have the same thing downstairs in both terms, and I can then combine what we have upstairs into one big final answer. And it's not going to be a beautiful answer, but we've gone this far. Let's just do that last step. So then everything is upstairs, minus sine x minus 2x sine x minus 2 cosine x, whole thing over 1 plus 2x squared. So as we've seen, when you take a derivative, usually the function you get out doesn't look as nice as a function that you put in. That's just the way derivatives are. And again, there's no need to carry out this simplification for the homework. The main thing is to know how to use the chain rule so you can at least get to here. All right, let's do one more example. F of x equals log of sine of 9 to the x. So this is a double chain rule. There's no product rule here. I'm not multiplying functions together. Rather, I'm chaining together a whole bunch of functions. So we start, the innermost function is an exponential, 9 to the x, and then that gets hit with a sine function, and that gets hit with a log function. So we start by taking this inner function, sine 9x, and we're going to call that blah. So we need to take the derivative of natural log. So the derivative of ln blah is just 1 over blah. So there's 1 over blah. Then I need to take the derivative of the inner function, blah, which is sine 9x. So now sine of 9 to the x is also a chain rule situation. Two functions strung together, not multiplied, but done in succession, one after the other. So I've got a sine to the blah situation. Derivative of sine to the blah is cosine blah. And then I need to take the derivative of that inner function. The derivative of 9 to the x is natural log 9 times 9 to the x. So this is a double chain rule. We have an outer function and an inner function. When we deal with that inner function, we see that that inner function itself has an inner function. But no big deal. We just keep applying the chain rule from the outside to the inside, and just keeping track of terms, and that's what we end up with. Not really a way to simplify this, and yet again we're seeing that the derivative is a larger function, more voluminous in terms of ink than the function that we started off with.